Hello everyone, welcome to the Exploring Machine Intelligence class, where we study about deep learning for artists. Today's topic is the sequential modeling, that is using machine learning models to learn sequential data and using various tricks to actually capture that sequentiality well. Okay, so the motivation for today is that quite often we may see some data in nature or in our data sets coming in sequence. So that is a moment where the frames of that sequence, the order of that frames actually matters. And so what we would like to basically do with that sort of data is having some model in there somewhere in the middle and learn or be able to sort of capture the sequentiality of the data by having a model which can predict the next sample from this sequential data. If you look at the data that we have here, you could of course sort of consider it as a block of data, and in that case take this data as a full-on block, and we could even use models that we talked about previously, so something like a CNN, convolutional neural network, or a fully connected neural network to sort of map this data, to map this X and Y and try to learn this relation there. But the problem here would be that the order sort of between the frames is kind of lost, because when using fully connected neural networks, this locality would be lost completely, and when using convolutional neural networks, the locality would be sort of maintained only in areas of the convolutional kernels. Whereas what we actually would like to sort of capture by that model that we would like to have here is the fact that we have some frames of data coming in sequence, and this frame is sort of depending on all the previous frames that came before it. And so there could be some information there which will sort of link into that. Okay? Well, so this might look a little bit abstract right now. We will show some practical examples as well with like text data and music data today. Okay, so the plan for today is to introduce the networks, which have some sort of recurrency, so they have some memory in the units of the networks, and then show some examples of using these networks with some text and music data. Because this is the 7th week recording, and the class is mostly over. The practical session that we will have on the Friday as a live session, it will be a Q&A session for the final exams. So it will not be linked with the stuff that we will be learning about today. It will be more or less focusing on the final exams and figuring out what will happen then and how to prepare for that as well. Okay, well, so to introduce what we will be working with today, well, we will be reusing a lot of the terminology from the other networks that we studied about. One difference from all the previous models is that in this case, we want to have some unit here, and to have that unit produce some output data from some input data. That's the standard sort of behavior. But also be able to for this unit, we want it to be able to learn how to change its own state depending on what comes on the input. And so if we see this sort of input, we want to the model to sort of analyze it, give us some output, but also change the state in a way to remember what is important from this one frame of data, in order that in the next frame it will be able to use that information from the previous state. And so this next frame will be processed with the information from this next data, but also from the kind of carried over unit states from the previous iteration. Okay, and so it should also give us a new data output. And so this sort of continues, and we sort of want to for this unit to parse through data, but also change something inside it. And as always, when talking about these models, this is the design, and all the behavior that we want it to learn comes from the data that we will throw at this. And so this behavior of being able to output something meaningful and then also to remember something meaningful and useful for the next frames analysis, all of that comes from the structure of data. So if there is some sort of dependence in that data, we have designed a unit which has this sort of behavior in the mind that it can actually access or save some information that would be useful for the next frames. So we are never writing this kind of encoding it exactly. By the design of these models, we are sort of allowing this behavior to be learned. Okay. Well, similarly, like in previous cases where we had a single single neural network unit, single neuron as a unit of a larger layer of neurons. In this case as well, we have a recurrent unit here, and we are sort of building a full-on layer from these units. And so it would be difficult to read schemas of models which have all of these arrows everywhere. So what people do is that they sort of write them down as a sort of simplify them into this glyph. So we have for example, a LSTM, which we will talk about later, one particular type of these units, a layer of these units, and we are remembering how many units we saved. And so the output will be one from every unit here, and the input connectivity is similar to the case in fully connected neural networks. So the fully connected layer of neurons. Okay. Okay, so there are various types of the designs of these units. I will not go too deep into explaining how they work exactly. There are at the end of this lecture, I will link to 2 blogs which will explain all the details about the simpler RNNs and then the later models as well. However, this is a visualization of this single unit, or this single well, this could be a layer of units, and it's getting a input information in time -1 and then outputting an information in time -1, and then sending a kind of unit state to the next iteration, which is this one, which is with time t, and outputs with time t, and the same with like later iterations. So this is a way how to visualize that, what I was trying to show in the previous frames slides as well. This sort of unrolling of one unit, which is recurrent, which is sort of saving something in time, so saving some information for the next frames. So what you can see here is that there is some function inside which is similar to the units we had before. There it was a sigmoid function and sort of connecting every input and weighing them down, all of that. Similar stuff is happening here, but we are not only outputting that information, we are also sort of keeping that information for the next iteration of the same unit. Okay, so this is a simpler unit design, because it turns out that that if there is a long-term dependence between the data that we are feeding it with, this unit will more or less fail. So let's see what it actually means. So these type of networks are used to capture text data, because text comes in a sequence, and you could say that a letter here is very highly dependent on all the letters that came before it. And not only that, not just letters, but even the words. And so I was talking about the dependence between the words. So for humans, it's relatively easy to read this sentence, and if you didn't know what we should fill in here, sort of, I grew up in France, I speak fluent X. So if there was a unknown thing to predict, for a human, it would be really easy to sort of say, oh yeah, somewhere at the start of this sentence they talked about France. Okay, hence this is probably French. But for these networks, I mean, you can feed these. We will see how we can feed these sentences in, so word by word or letter by letter. But for the network to remember this sort of dependency or to remember this this relation, it has to be able to capture these long-term dependencies. So it has to be able to maintain this information somewhere inside its memory, something about France, even if we are parsing through a really long sentence here. And so it can happen that if we have a long sentence here, something like inbuilt there, some really strong story, or really long story, then we get to the end, the network has already forgotten about the information it stored about France. And so there is sort of a response for this was a design of a more complex unit like this, and that unit is called the long short stem memory unit. And these are way more complex, and they are made to remember longer dependencies inside this data. So again, I will not go into the exact details, but we have roughly like 4 times the blocks with some parameters which are trained. There are even more than 4 times the amount of parameters actually. We have some sort of gates which these inputs and these memories from previous iterations go through, and so these forget gates and input gates will control A, what the network is remembering for the next frame, and B, also what it is outputting for this frame. And so it is a more complicated model to sort of train. It has more parameters, but it's also able to remember better these long-term dependencies. Okay, well, outside of this sort of, it's almost the detail of how it was designed, the behavior is more or less the same. So we will again have some unit that we are feeding inputs in a sequence, and we are sort of expecting outputs from that unit at various points of time. Okay, well, let's see how we can plug in some text data into this. So the first example will be working with letters of a sentence. So if this is our sentence, I grew up in France, I speak French. And let's imagine this is not just one sentence, but this could be a whole data set of maybe Wikipedia articles, or maybe the whole corpus of text from Shakespeare or something like that, right? So this is a simplification of just working with one sentence, but you can imagine that there could be any other textual dataset. So we will need to sort of vectorize this input into something that we will be able to process with models. Okay, so we could convert every letter into one single digit, but then it's not really clear why 2 digits next to each other would be similar, right? A, B, these 2 letters have nothing in common, but the numeric value is really similar, really close. So what we use instead is something we saw before as well, is the one-hot vector representation or encoding. So if this is the original data, then we will encode this sentence using this sort of process. For each letter, we will find it the position in some sort of dictionary. So for alphabet, it's easy because we already have a dictionary called alphabet. But we will see that there are some special signs, like maybe even space actually. So we will need to maybe add some new signs into that dictionary. So for each letter, we will sort of assign it with the value of the key inside the alphabet, the numeric value from the alphabet, its ordering. And so we will place a 1 here and then zeros everywhere else. And that is a vector representing a letter I. There are 2 sort of additional signs I added for this sentence we are parsing. There are a lot of dots. So dot is 1, let's say, additional entry inside the dictionary, and then let's say a space is another one. So we have 26 letters in English alphabet plus 2 of these special signs. We could encode this entire sentence into this dictionary. So this is what we do. We basically convert letter by letter the whole sentence, and from k letters, we would get a k by this dimensionality that we chose from the size of the dictionary. So k by d, which is in this case, in this simple example, 28, block of data. And this block of data corresponds to this sentence. I grew up in France. So each single letter was encoded as a one-hot vector. And this was simple because we were just working with letters. If we had another task to encode full-on words, we would have to create a dictionary of words, which is also possible, and it is actually being done more than just working with letters. But we will start with that because it's simpler. Okay, and another sort of fact from being able to use this encoding into a dictionary or into a vector of one-hot vectors is that at the end, when we will get some predictions from this model, we will be able to use this dictionary sort of as a lookup table and to decode these predictions back into letters. Okay, so let's see that more concretely. If we have a data set like this, where this is the encoded sentence, I grew up, etc., we have encoded them as vectors. So this is k letters times the size of the vectors, so k by d block of data. We can consider these consecutive frames as sort of the x and y that we are learning, right? And this will be sort of jumping around, because what we want from the model is to learn the sequence. We are training a simple model where this simple model is for example, a LSTM model here, where we have, for example, 28 units, but this is more or less arbitrary, right? There could be any model. But the size of the units will correspond to the size of the output, so this should correspond. But in real life, we will use multiple layers, and there might be different types of layers as well, so this might be more complicated. As I was saying, we are trying to learn the sequence, and in order to do that, we are trying to train the model to learn the transformation from x to y. While one thing for this model to learn is to predict from whatever this x, this I, encoded vector, to predict that the next letter will be this y, so this encoded letter, a space. And the second thing to sort of we want this model to learn as well is that it should remember some important information that is useful for the next iterations. And so in this first sort of iteration, we are showing it. Well, this is really just going through the dataset actually, and I'm showing the different samples we have there. So this would be the x1 to y1. The next iteration would be the space character as x2 to g character encoded into a vector as a y2 vector. And we are sort of learning the dependency between these two. So not only that a letter I is often followed by space, but also in the case that if I is followed by space, maybe it's important to keep something in the memory of this network that will guide us about what is the next possible letter that this thing will continue with. So if we have a space, we know that another word will sort of continue, but maybe there is a limited amount of words which can continue after seeing a y and then space and then next word, right? So I have, I will, I should, I don't know, right? So there is a limited set of words, and the probabilities for some of these words are higher. And so this is something that we want this model to sort of capture inside its own loop to sort of figure out what it should remember from the previous frames. Okay, well, and so we continue with this. We will be showing it data from the G to R and then R to E as different data samples for this model to learn. This will continue all the way up until the end of this sentence, where we will have some sort of end sign and stop sign, where this model will learn, okay, after this there is an end. So this could be a dot, but more often it's a special character called something like end, and it will just stop that sentence. Okay, well, so this generation task is called many-to-many because we are sort of trying to feed in many inputs, and at every iteration of this thing we are looking at the output of it, but also at the end we want to sort of reconstruct the whole pack of outputs it had into the predicted word. So one thing that this is used as is the prediction of letters to the next letter predictions, sort of generative models. But another type of applications for these would be a translation model. So you would have a language of one kind on one side, and then sort of the corresponding translation on the other side. And this would be more common with not just letters, but full-on words, where we would encode full words into these vectors. And because that's a difficult task, because we don't have a one-to-one correspondence for every word in every language, right? So some sentences in one language are more concise, while other languages tend to be more, use more words to capture the same information. And so that is a many-to-many transformation, but we would have to use some models like this. Okay. Well, so this is just a simple example where we have a single layer and we are learning it on the data from the letters. So one sample follows to the next sample, and this goes on and on until we sort of reach the sentence, the end of the sentence. And we would learn this over the whole data set. Okay, so this is an example of a very simplified data encoding. So we have these are the inputs coming into this one single unit, and the unit is outputting a output for each iteration, but it's also sort of sending itself the information for the next frame. So something important that it should sort of keep in mind after seeing age. And this sort of means the next frame, where we are reading another input, and it tells us what to. It mixes with the information from the previous frames and predicts a next letter, but also keeps something for its own into the inside the unit. And so this is basically feeding in H, which produces E, which produces L which produces L, with this sort of sequence having been encoded here. L with all of this information accumulated here will produce another L, and then this will be followed by O. So this is a simplified example where we had a just few letters, small dictionary as well, and a model which is predicting letter by letter. We didn't go too much in depth about what's happening inside these units. So how does it exactly work that it's remembering something and then it's sending something to the output? Well, all of that is in way more detail included here in this blog by Andrei Karpaty, which is about the RNN effectiveness. I will link to that at the end of this presentation. It's really useful for understanding the details of this, and also for a lot of visualizations that they have there. Okay, so let's not just stop with text data, even though, as you can actually see on the blog I was linking to, there is a lot of use a model which is predicting sentences and characters, text information. There is a lot of power in that model as well. So the reason being that you can encode a lot of things inside text. So you can consider, for example, coding, just writing programming code, as being a text dataset. You can consider dataset of literature written by certain authors as being a dataset. You could consider a dataset of articles as being a dataset of text as well. And all of that includes a lot of complexity. But let's sort of show another example of how these models can be used, or where else we can see some sort of sequentiality. And so I'm talking about music data, which is a type of data which in its raw form has a lot of information saved in a very in many frames. So if we encoded music as a 44.1 kilohertz sampling rate or something, we will have 44,000 values for 1 second of recorded material. And so there is a lot of redundancy probably going from one frame to another in that form. And so for practical reasons, this is something that we wouldn't really train on because it would be really hard to remember anything about this information here when we reach to 1 second further, because we have passed over 44,000 samples already. So the long-term dependency would be even more problematic. So we use a spectrogram representation, which is using the Fourier transformation, segmenting the music into various bands, sort of the frequencies on this axis, and then time on this axis. And so it's a sort of compression encoding that we can use to consider what the music data to be encoded as a sort of image representation. What we will also get is that the dimensionality of these vectors, of these values, will be something which is fixed. So it depends on the setting that you would use for the FFT, but you would get roughly like this amount of numbers for each frame, for each unit of time. There is some amount of parameters you have to decide for when using FFT, but yeah, that's sort of besides the point. We can use this as an encoding step to convert music into a blocks of data of frames by vector dimensionality blocks. And furthermore, we can sort of use this representation, we can train on this representation and predict in this representation, and then at the end we can use, we can go back from this representation by decoding from spectrograms using the inverse FFTs. So there is some amount of complicated problems there, because we are going to lose some information in the process. However, we can sort of take that as a useful intermediate representation, these spectrograms, to handle music in a better way for these models. Okay, well, so we ended up with a dataset represented as these blocks of data, which was similar to the way we represented the dataset with text vectors. And in this case, we have a block of K by D dataset. And we are going to train a larger model on this. So this is a different type of a setup. We will be training the model on a longer sequence of data. So for a sequence of 40 frames of this original dataset, of this encoding, right? So this is 40 frames from everywhere, from basically anywhere in the dataset. We want this model here in the middle to learn the dependency between this input, these 40 frames, and the 41st frame, so the next frame for this sort of block of data. So it's really a next frame prediction model, this one. And so this is called many-to-one, because we are going to feed in frame by frame all of these inputs, and then kind of ignore all the intermediate results in the process, but look at the output of the last iteration. So after feeding in everything, we will look at the output of that last frame. Okay, so we are again learning a correspondence between x and y. So we processed the dataset by splitting it into some amount of blocks and the next frame prediction, and then we will be training this model on this relation. So let's say that this model was able to capture this. So if we use this model and give it a block of 40 frames, it will generate to us a reasonably well-working, well-sounding next frame for that sequence of 40 frames. Okay, and so I was sort of it's modeled here as a LSTM model, as a simple LSTM model, but somewhere in the background, I worked on a project which was using a slightly more complicated model, which was using a LSTM or 3 layers of LSTM units. We mixed in a dropout layer. We mixed a fully connected layers at the end, and but basically we were matching this type of data. So given a sequence of 40 frames, I wanted to predict a one next frame. Okay, well, if we have this model, we can jump into the data and like find one moment to start at, and we can call this a seed. We throw in these 40 frames as the original seed. We will get the next frame, and we can then use this next frame to append it at sort of at the end of this input. Again, I guess forget the first frame we fed it. Append this as a new input and use this new block of data to predict the next frame. So at this moment, we are just using this trained model. We are no longer trying to train this correspondence between the data. So all of the so this model has already trained how to predict the next frame samples, and also B, what to actually remember from this data, which will be useful for next frames, for the overall precision of that model. And so that is not being changed, neither one of these two behaviors, that is fixed, but we are changing the states of these models with every new frames we are giving it, and we are also getting new types of information from new inputs. Okay, well, so we will chain this model, and then using this same setup, we will get the next frame, and then following the same setup, the following frame for this sequence. Well, and so you can start seeing that if you chain this model and sort of reuse this same model again and again with the data, and every one of those iterations is giving you one next frame, you can start combining these frames, these generated frames, and call them, hey, yeah, this is the generated music. So yeah, basically, I actually was working with a model like this, and we have some samples to show how this music sounds in the end. So I will play it. There are two things to sort of see or to understand. Two important things to sort of understand before listening to it. One is that we found some part of the song and then started at that part of the song. The song is trained on like one, I think 10 minutes song piece. So there is enough information for the model in one song to actually be able to generate sounds from that song. So we will hear that soon. But we have started at somewhere real. So we started in a real place of that song. And what can happen in this iterative manner is that we can get into a loop where maybe this next frame, which would be generated here, is something which is really similar to this thing. So maybe we would sort of get stuck in this sort of loop, and then this model would be, I guess, basically stuck on a local minimum where it's not able to jump from that space because it's always generating the same thing. Well, so in that moment, what needs to be done is basically detect that moment somehow and jump in space somewhere else, seed it with some new data, and then the track will continue. So I think in this sample, this happens once, where the music becomes really repetitive. That's the problem of getting stuck in a local minimum. So yeah, let's hear it. So I will just stop it for a bit. I think here, whoops, here was the moment where it got stuck, and I think I had to move it somewhere else to sort of get it unstuck. Okay, so well, this is part of the project I was working on at CCI. So there is a bunch of other samples of musics that are to be looked at and to check. So if you'd like to see more about this project, you can look at this repo, and there is a lot of code which just basically supports some model, basically the simple model that you saw in the slides, and it's using that model to interactively well, it's using an interactive interface to sort of use that model to sample new music. And so this is relatively raw output. You can see more of these raw outputs at this page here with the demos, and you will get a bunch of different trained models on different trained pieces of music. And this is a yeah, just the raw outputs basically. So a lot of them will be actually bad. Even on these visualizations of the spectrograms, you could see it because there is a moment where something interesting happens here. So this is the patterns from the original song, or this is the patterns from the original song, but you can see where it's similar or where it fails. So here it clearly failed on some stuck. It got stuck on some area. Yeah, and so the recreation is not perfect. For example, this generated jazz is sounding really different than the original song, than the Brad Meldau's "Don't Be Sad." But it's sort of interesting because you can see some, or you can hear some patterns from the original song that it also sort of deviated from that. So yeah, okay. So let's get back to the slides. This is a slightly more complicated example of a use of a model which would be trained. We could use some different types of data there as well. I guess the important kind of concept here is that the LSTM unit can be present in any sort of network where you are feeding in a data in sequence. So you could have a huge model which is processing some image, some frame from a video, compressing that into some smaller intermediate vector representation. So maybe like 4096 vector sized stuff features which were embedded using a model, something which would be something like a AlexNet or a VGG16, something that we have seen in the previous classes, right? We could use that as a encoding of an image into a vector, and then feeding that vector into a LSTM of this type. And so, and also the data that you would be outputting at that moment could be all sorts of things. So people were training models which were able to maybe describe some information on an image. So it's a or on a video, sort of video summarization from multiple frames. It will extract some information, use these sequential models, and then predict some data from that. Well, so we can look at like roughly look at the all types, all possibilities for the types of models and the data schemes that we can use. The one-to-one modeling is the one that we worked previously with. So you have one input, you want it to train one output. That's the standard. Basically, any other model, all of the CNNs, all of the fully convolutional neural networks. In that point, the model is basically frozen, and we are never changing anything inside that model. Whereas all of these other designs somehow are including information inside, sort of replicating information from inside that unit, either by feeding in different frames in sequence or doing something crazy like this. And so if you're at all interested in this slide and what all of these mean, you can again check the illustration here. I mean the blog here, which explains it in more detail. Okay, so for we are near the end of this class. For this week, as it's our last content week, let's say the last week where we are actually learning about something new, we will not have a practical session, the usual practical session where we would be working with the code. We will be instead doing some Q&A session. So I think that will allow you to ask some questions about something that you might be not super clear about, and I will also try to add in some information about the possible topics that I could be asking in the final exam. And you can roughly imagine that it would be like a little bit from everywhere, and I will be more or less focusing on the concepts rather than some tricky details somewhere, which are not that important. So if you want to read up on how the assessments will work, there is some part about that in our Moodle page, but we will also talk about that in our live session. Okay, I guess today's session was relatively shorter, I think, but if at all you are interested by the concepts behind modeling sequential data, well, in terms of modeling text or even modeling something more complicated, which would come in a sequence, I would like to recommend these two articles or these two blog entries. They are really readable and really cool. The first one, which sort of, I guess, started the craze around RNNs, Recurrent Neural Networks, is the Andrei Karpathy's blog entry called "The Unreasonable Effectiveness of Recurrent Neural Networks," and there is something magical about RNNs. This post is about sharing some of that magic with you. We will train RNNs to generate text character by character and ponder the question: how is that even possible? Because it's somewhat surprising that these relatively simple models can learn stuff like that. So yeah, this is a cool thing to start at. And if you would like to learn a bit more about the LSTMs, so the long short-term memory models or networks, you could continue here. Besides being a sort of follow-up on this article, it also includes a lot of really nice illustrations, which will make it clear. Even the basic understanding of RNNs will actually it will help with that. Okay. Besides that, I think there are quite nice samples of generative of the text that they generated in this article. So they were generating LaTeX, for example. So being able to generate something which then can be converted into a page. So text is only an intermediate representation there, or code samples and stuff like that. Not that it would work, but still, it's interesting. Okay. Well, these would be the articles to read about the theory. If you want to have a bit more hands-on experience with with sequential models with RNNs and LSTMs, there is a really good repo called Word RNN, which includes model to train for word representations of datasets. So I think there is the first demo that you would see here is a model which can be trained on a dataset made from the Shakespeare corpus of texts. And so, practically speaking, this is also relatively easy to just rewrite a little bit in the code, in the runner function, and retrain it on your own datasets. So I think it requires only one file on the input, like one input file as a text file, and then you can just run it, train it on that with various setups of the sizes of models and see what it generates. Okay, well, all of that that I was talking about today was mostly focusing on the generative nature of sequential models. So how to use these models which are used for language modeling and stuff like this, how to use them for generation. But if you were interested in more on the side of the text analysis, you could look into the GenSim library. So that's a relatively easy library, which is a Python library which allows you to work with analyze text datasets. Yeah, sometimes also using some deep learning, sometimes using some different methods. But yeah, I just thought that it might be useful to link it here as well. Okay, so with these links, I think this is more or less everything. So I hope you liked today's class. It was a little bit shorter one, and it's just an overview of a new domain of models, but I still thought that it might be useful to learn about them in this class as well. Okay, so see you in our live session, and yeah, see you then.